Hey everyone, so this is going to be the second unit, which is all about dynamics, forces, and things like that. Now, in addition to kinematics, this is also a really big unit. It covers a lot of material. So, unfortunately, we had to kind of cover this stuff a little bit earlier, and I may not be able to get all this within this first quarter. So, I apologize for that, but this is a fairly big unit. Now, I will say that most of the material that we're going to cover in this set of slides, the 2.1, not necessarily this specific video, will act as the foundation for all of this entire unit. And not just this unit, but this course as well. What I mean by that is that a lot of the other stuff that we're going to have to cover are more scenario specific, while this is the general stuff necessary for Newton's laws and dynamics and force questions. All right, so we're going to start off first with just a basic info dump about everything about forces and basic stuff. So one of the big things was this was kind of pioneered by a famous scientist called Sir Isaac Newton. Sir Isaac Newton also developed calculus, so blame him if you have any issues with either physics or calculus, because it was all due to him. Um, and basically he came up with the definition of a force and all these very important rules as far as forces and how they work. So a force, the definition of force is that it's an action or interaction that causes a change in motion of an object. So what do we mean by a change in motion? um, it typically means increasing the speed, decreasing the speed, or changing the direction. In other words, a force is anything that would cause an acceleration. So another way of saying this is that a force causes acceleration. Objects will accelerate when experiencing a force, when exposed to a force. Forces are vectors, so this means that direction matters. Force to the right is different from a force to the left. This also means that forces can be positive or negative, and forces are measured in the unit of newtons after Sir Isaac Newton. Um, so interesting thing about units, which I'll say in class. Please remind me about that. Now, there are four fundamental forces in this class, or not in this class, in physics. The first is gravitational force. Gravitational force is a very long range attractive force. Technically, it is infinitely long that acts between two pieces of matter. It's one of the weakest of the forces. Now, I do want to point out that recent discoveries have found that this really isn't a specific force, an individual force, it's something else. But as far as we're concerned, in order to do the problems, we're going to consider it a force to make life easy. The other fundamental force is the electromagnetic force. This is the force between electric charges and magnetic objects and magnetic effects. This could be the repulsion effect or an attraction effect. This is also long range, but is extremely strong, much stronger compared to the gravitational force. With gravitational force, we don't experience it unless we're at the size of celestial objects like moons. But the electromagnetic force, we only need a few charges, and then we can already see the effects of the forces. Now, the other two are not really ones that we talk about. You kind of need to know them, conceptually, but they're not going to be used. They're only found at the nuclear level. One of them is the weak nuclear force. This is one we definitely don't talk about. This is really short range, and it's responsible for radioactive decay. And the other one is the strong force. Very creative with their naming, I know. This is the strongest force, and is responsible for holding the nuclei of the atom together. This is the only thing you need to know about the strong force. It is what keeps all the protons inside of the nucleus. Because remember, according to the electromagnetic force, which we'll talk about when we move over to the Regents material, the electromagnetic force wants to repel these two like charges, two positive charges, but the thing holding them together is the strong nuclear force. Now, there are other forces. Technically, the forces we talk about right now, the ones that we end up using the most in class, can technically be part of one of these other four. They're actually almost all exclusively electromagnetic forces, except for the one that isn't, which you'll see. But they are technically subsets of these other four fundamentals. They're just the way we see them, we kind of give them new names. So first one is the force due to gravity. I wonder which fundamental force this is related to. This is represented by Fg. It is the force that keeps us on Earth or connected to any planet. And it's something that is always present. It's always present acting on us. And this is sometimes referred to as weight. You want to make sure that you keep this in mind that the force of gravity is also called weight. This is extremely important because a lot of times they say the word weight, and students will accidentally confuse this with the term mass because in like the way we use it in society, we use weight and mass interchangeably, but that's not the case. Weight is force due to gravity. Mass is something completely different. The next one is normal force. This is the contact force that we experience whenever we're touching an object. The reason we call this normal is because it always acts perpendicular to the surface. What do I mean by this? So if I have a surface like this, so this is my floor, and I have an object on it, the force will act perpendicular to the surface from the point of contact. It is contacted, this is the point of contact, this section of the object. So the force acts this way and goes up. It's always pushing away from the surface. If this was on a ramp instead, it would do the same thing. We'd have our object like this, and it would act normal to the surface, perpendicular to the surface. One thing to point out is that notice how these have subscripts. Every force is F, but there's a subscript attached to it to tell us what specific force it is. All right. The other common force is tension force. This is the force caused by pulling from a rope, string, or cable. So if you have an object that is attached to a string, then there's a force going to be related to that, pulling from that. Easy enough. It kind of makes sense when you really think about it. It's pulling in that direction. The applied force, which we subscript as AP, is the force essentially any person applies to an object. Technically, this could be anything. Applied force just means anything that acts on an object, but the way we end up using it is referring to a person physically touching it and pushing it. The key thing, though, is that the person has to be physically touching it in order to have an applied force onto it. We'll see a bunch of examples of this, but one example that I can give is if we had a table and we have a book on here, and then a person, this is the hand, there's my great hand, the person pushes their hand down. Now, because this box is connected to the table, this force will indirectly push on the table. However, if we were going to draw the forces on this table, we would never draw this applied force because this applied force is only acting on the block because it's only touching the block. It is the other forces that are acting on this would be something like the normal force that's acting on this. But we'll talk about that in more detail later. But the idea is that unless you are physically touching an object, you are not applying a force on it. So, like I said, the person could be pushing or pulling an object, and that's how we use it. The other common force is frictional force. This is one we're going to talk about later on in more detail. This is the force that opposes motion, and it's basically when two objects, two surfaces are touching and essentially sliding around on each other. So this one's actually also a contact force, just like the normal force. This is assumed not to be present unless told otherwise. Now, there is one caveat to that, and that is that if the scenario wouldn't work without it, then we can assume that there's friction. Again, we'll see examples of this later on because right now, if I try to explain it too much, it'll kind of be a little confusing. But if we had an object that was on on like a car, a truck, like this, and the car started moving, and this block remained connected to this the truck, that wouldn't work unless there's friction. So that would be a hint. Okay, there must be friction acting on this box. So just wanted to throw that out there. That there are scenarios where you can look at it and say this wouldn't work without friction. Therefore, there must be friction on it. Centripetal force is something that we'll talk about more detail later on. I think this will be the next unit. This is the force that acts on an object moving in a circle. Centripetal means circle. These are some not as common forces. What I mean by that is these are very niche. The ones that I said before can be thrown into any problem. Friction, normal force, all these will be used a lot. But gravitational forces is a very niche force. This is slightly different from force due to gravity in the sense that the equation that we use is different, but it technically is the same thing. This is the general attraction of any two objects based off of their mass. Force due to gravity was specifically from a planet, like when you're on the planet Earth, on the planet Mars, that is your weight, that is what you feel. The gravitational force would be things like either between two people or maybe between a planet and the moon or Earth and the sun, things like that. So gravitational force usually refers to planet-like objects. That's when we use it. Electrostatic force, this is something that we'll talk about in the Regents material. This is the force between charged objects. Again, could be attractive or repulsive. Magnetic force is one that we talk about conceptually. There's no equation that we use here. This is between magnetic objects, magnetized objects. Again, could be attractive or repulsive. All right, so those are all the forces. Like I said, if you didn't fully understand them, don't worry. We will go through and see them in a variety of different ways. So you will very quickly learn them. The other thing that I want to mention is what's called a free body diagram. You actually kind of already saw me doing these when I was doing my little diagrams. But this is something that you will have to be able to do, both in order to do problems for yourself, but also for questions that they ask. There are going to be times where they want you to either identify the correct free body diagram or draw a correct free body diagram. So this is extremely important, and it helps visualize the forces acting on an object. So free body diagram, or FBDs for short, are very quick sketches free of outside supports that show the direction of each force acting on an object. What do I mean by that? So let's say that, actually, I think I have a question here. So here we have a fireman lifting a little boy out of a well using a rope. The boy weighs about 500 newtons. Let's say we want to draw an FBD of the forces acting on the boy. So I didn't clarify that, but this is on the boy. Well, if I think about it, first thing I want to do is start with the box. We're not artists here. So I know some of you may be, but we don't want to spend that much time on this. So everything's a box. A boy's a box. A car's a box. A box is a box. A wheel is a box. Everything's a box. You start with a box, or sometimes a dot. You start with a box, and then we draw the forces. Now, there's one force that's always acting on them, which is the force of gravity. So they told us that the force of gravity is 500. So we know that this, the FG, is going to be 500 newtons. Now, because the boy is attached to a rope, we also know that there must be an upward force pulling him up, trying to get him out, and this is going to be the tension force, like this. Now, here's the thing. The fireman is pulling on the rope, so you might be thinking there must be an applied force. But again, the fireman is not directly touching or lifting up the little boy. He is lifting the rope. He's pulling on the rope, and the rope is pulling up the little boy. So the boy doesn't get the applied force. The rope technically gets the applied force. The boy only gets the tension force. So yeah, this is what I mentioned. Now, after you do this, you usually like to add in what the values are. So that's what you saw here, where I wrote FG equals 500 newtons. All right. So here, let's do a practice question. Pause the video, work itself, and we'll go in a second. All right. So we want to draw an FBD for the egg while it's in free fall. First one, we're going to neglect air friction. Then the other one, we're going to put it in. So easy enough. We're going to draw the egg. The egg's a box. We draw a gravitational force going down. That's it. There's no other force acting on it. We go through everything. Nothing. For the one where there is air friction, while it's in free fall, it's going to have the force of gravity pulling down, and then the air friction pushing it up because it is opposing the motion. Now you may think, wait a minute, you didn't have this as a force. Technically, you can put any subscript on your forces. The subscripts I gave you were the common ones, the typical ones, the ones that most people use, and the ones that I'm going to be using, so that you're not confused when you see FN and FT anywhere. But you can always put a subscript no matter what it is. If you want to label something as the force that the truck is applying, you call it FT or F truck. You may not want to do it FT to not get confused, but it depends on the problem. All right, here's the next one. Pause the video yourself. I'll go in a second. All right, so we want to draw the FBD. So again, we start with a box. The box has a force of gravity pulling it down. We have two ropes, one directly to the left, and then one going to the right at a 30-degree angle. So the one to the left goes there, And then the one going at a 30-degree angle would look like this. I do want to make sure I include the 30 degrees because this ends up helping me kind of, again, visualize the forces. And one thing to notice is that we had two rows, meaning that we have two tensions. I would not want to label them as both FT because then I'm going to get confused when I'm doing problems. So I do FT1 and FT2 to differentiate between them. So when I'm doing problems later on, I know which FT I'm talking about when I'm looking at the problem. All right, here's the next one. Pause video, works off. We'll go in a second. All right, this one's an easy one. They want us to figure out the normal force, which one represents normal force. Normal force always acts perpendicular to the surface like that. So the only one that even comes close to that would be choice 3. Now there is one last thing that I want to talk about when it comes to FBDs, and that is to make sure that when you draw the arrows, I said that they're quick sketches. However, you do want to make sure that you reflect certain forces that are supposed to be bigger by making their arrows bigger. This is important both for yourself, but also some of the later questions that you will end up seeing where you actually are tasked with drawing an FBD. You will have to make sure that if you know for a fact that one force is bigger than another, that you represent that in your FBD. Um, so, if you know that your forces are unbalanced to the left, you would draw the left arrow to be much bigger to show that it's unbalanced. Now, there is something that they'll end up doing where they'll give you grid lines. I apologize. I'll show a better example in class. So you'll be given grid lines like this. Maybe I'll add a few more grid lines going up and down. And let's say you drew lines. You would have to make sure that you'd have a line going to the right that is exactly one box to the right, and then one line going to the left that is two boxes to the left. Does it have to be exactly this? No, sometimes, there's not going to be a specific rule that this arrow has to be exactly this number of boxes, but the idea is that it has to be representing a bigger arrow on one side. And in order to make sure that it's very clear how much bigger it is, they give you this grid paper so that you can have specific points to make sure that you end on. We'll see a bunch of examples like this later on. It is extremely important that you know how to do this. And a lot of kids end up struggling with this one, and you'll see why when we go over it. But that's pretty much it. The free body diagrams are extremely useful to doing problems. Like I said, pretty much every problem we do, the first thing I'm going to say is draw an FBD. Especially if you're asking and you're saying that you don't know where to start, I'm going to say draw an FBD. The FBD is extremely crucial to doing a lot of these problems, and without it, without being able to set it up, you're going to get lost along the way. All right. So that's basically it. So like I said, it was just a quick info dump about everything with forces. Pretty straightforward. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.